Everyone, good morning. So sorry I couldn't be there today, but the idea is that we're trying to get ahead in our next unit, and our next unit is energy. So your agenda for the day is to first listen to me talk about energy a little bit. We're going to try a couple of calculations, and then we will go from there. So, how I always like to start with energy is I always first talk about roller coasters. My favorite roller coaster at Six Flags is the Boss because obviously, but Screaming Eagle, Ninja, stuff like that, they all have something in common. So whenever you look at these two pictures, I want you to just pause the video and think for a second, make a hypothesis. What is the aspect that these two roller coasters have in common? So I'll give you a couple of seconds. Three, two, one. Anything? Hopefully? Alright. Well, the idea mainly is that, notice, even on, I think this is what, Screaming Eagle? On Screaming Eagle, you can see that there's always that, like, click, clack chain that goes up to the very, very top. Same thing with Boss, is that the main thing is that the highest point is always at the very, very beginning. That's the idea. So they're always trying to do something, but the highest point can't be like past. Of if the Boss had, a point like 200 feet up, and then it had a loop-de-loop and all this other stuff, and then another had another hill 300 feet up, you would just be stuck in that gap, the middle there. So what exactly are they trying to achieve is always my question. And students a lot of the time are like, oh, they're trying to achieve height. Well, yeah, but what does the height do? Well, the main idea here is that really they're trying to make sure that they have enough stored energy to make it to the end. If, once again, the highest point wasn't at the very top, then they wouldn't have the more energy in order to make it to the end. Think of it like raising a bowling ball. Of course, if you raise a bowling ball 1 foot, yeah, it's going to hurt if it falls on something, but that's a whole heck of a lot different than if I raise a bowling ball like 30 feet, because you're adding more and more energy the higher up you go. Now, I keep on using this word energy. Oh, energy, energy, energy. Well, let's talk. Energy is the ability of us or a system to do work. Now, you think work of like physics versus just everyday work. Oh, doing like homework is an aspect of work. My parents going to their profession is an aspect of work. However, physics work is something very, very specific. It means the ability for an object to move in the same direction as a force applied. That's it. So it doesn't, okay, it's not saying that, like, as soon as the object starts moving, that work is being done to it, but it's the ability for an object to move with any forces applied. So, force of gravity, force of friction, that's the ability to do work. And it has stored energy. So, it's us or a system to do work. Now, our roller coaster, once again, whenever you are moving this roller coaster upwards, you are adding potential energy. You're trying to store as much energy as possible, and we call that gravitational potential energy. But once it starts moving, you have kinetic energy, which is the energy of movement. Now, once again, anytime we're doing these screen lectures, please feel free to just pause the video and keep on going in order to take notes of what I'm saying, and we'll go from there. So these are the main two types of roller coasters, or of energy that like a roller coaster is going to have, is gravitational potential and kinetic. Gravitational potential is stored energy from height, and kinetic energy is stored energy from movement. So that's the idea. Okay, so as I said, potential is just stored, but oh my goodness, there are so many different types of potential. It's kind of funny. I want you to be able to recite and repeat three for me. The main one we're going to be talking about is GPE, gravitational potential energy. Then you need to know like elastic, springs, rubber bands, rubber. This is like the way that sports balls are going to move quite a lot. It's because you're storing elastic energy on impact. So you have elastic energy, and then finally you have chemical energy, which is just energy stored in chemical bonds. It's the reason why as soon as you heat something up, then it starts releasing things of, there's lots and lots of different types of potential energy. So just an example of each, gravitational, once again, would be like lifting a bowling ball more and more and more. Elastic energy would be if you take a rubber band and if you stretch it, about 2 inches, as opposed to if you stretch it all the way back of like a foot and a half. Chemical energy would be like gunpowder, something of the sort. Of as soon as you light it, it releases those, and breaks those bonds, releasing energy. That's the idea. So all three, gravitational, elastic, chemical, are really, really important forms of potential energy. But then you ask yourself, well, where does this energy go? The idea is that let's first talk about GPE, gravitational potential energy. And GPE is always an equation. Of course, it's physics after all. But this equation is really not that scary. M times the acceleration of gravity times the height. So mass times the acceleration of gravity times the height is GPE. So let's try a couple of GPE problems. Now, whenever we try a problem, one of the main thing, once again, physics always likes to have weird units. The units for energy is called joules, Joule. It is 1 Newton applied by 1 meter. It's the same idea as the ability to do work, is that you want that object to be able to move. So anytime you're doing energy calculations, you are going to have a joule at the very, very end. So let's try one problem. We're going to solve for how much potential energy does this climber have. Now, once again, set it up exactly as you would. Start with the equation. GPE equals m times the acceleration of gravity times the height. And then you just start plugging in your knowns and unknowns. The mass is 70 kilograms, the height is 1450 meters, and the acceleration of gravity is at 9.81. So whenever you set this up, these types of equations aren't that, terrible. They're not that scary either. Everything's just multiplied straight across. I don't really feel like I need to go and show you how to multiply, 3 values together. So I just did it on my calculator, and you get 995,715, but with 1 sig fig, you would get 1 million joules. That's the idea, is that you're trying to figure out exactly how much energy. So as we continue, just think, is 1 million joules a lot? Is it a little bit? Well, look at his height, for goodness sake, 1450 meters. If you fall from 1450 meters, there ain't no coming back from that. That's how much energy you are supposed to have. So, then next we have kinetic energy. And kinetic energy, as I said, is the energy based off of motion. So it is based mostly off of mass and velocity. And kinetic energy is equal to the mass times the velocity squared divided by 2. So one of the things that you got to be careful about with this equation is that squared velocity. It's going to take the meters per second of velocity and turn it into meters squared over seconds squared, which we have never worked with. But then if you multiply it by kilograms, which is the mass, then you get newtons times meters, which is what you want for kinetic energy. So let's take another problem for kinetic energy. Once again, here, the only thing that I really, really want you to be sure of is that when you do this problem, pause and square the velocity first. That's the main idea, is that you want to square the velocity first because, please excuse my dear Aunt Sally, exponents comes before multiplication or division. So in your problem is kinetic energy equals mv squared over 2. You take 12, square it to 144, multiply it by 1300, divided by 2, and you need 2 sig figs, so this would end up being 94,000 joules. So some of the problems right now, not too horrible, I understand. So let's keep on going. One of the things I really like about energy and that I want to show you is, let's go to our roller coaster real quick, is that GPE and kinetic energy are basically two of the same coin. So let's just play this roller coaster simulation I found. I want you to look. So the red is potential energy and the blue is kinetic energy. So as the roller coaster keeps on going, you see, and let's see, that instantly once it goes over this hill, or any hill, it gains potential energy. Once again, the highest point is at the very, very beginning. As you take a step forward, if you go to step 1, it's going to be all potential energy. It's storing as much energy as possible. And then if we go into 2, then it's almost all kinetic energy. But there is a tiny bit of potential there since they are off the ground. 3, same thing, almost all kinetic, but a little bit of potential. 4 is going to be more potential, less kinetic. 5 should be a little bit of potential, little bit of kinetic, but it says all kinetic. And then finally 6 is once again a little bit of potential, little bit of kinetic. So this one starts, looking at exactly what it is, but I like the pendulum lab a whole heck of a lot more. So what this pendulum lab is that it's literally just a pendulum, and you can see off on the side here that it is a graph of the total energy, the energy due to thermal, the potential energy, and the kinetic energy. So as I pull the pendulum back, my potential energy increases. And as I let it go, what ends up happening is that it is going to switch back and forth of when it's in the very, very center. And let's slow it down, that the very, very top has the most potential, the very, very center has the most kinetic, very, very top has the most potential. It's always flip-flopping between the two of potential kinetic, potential kinetic. Now, one of the things that I want you to take a look at is this energy total graph. The energy total graph changes of that the energy for, all of the potential is a little bit, all of the kinetic is a little bit, but the total value of all the energy stays the same. It's saying that it would be like 1,000 joules. Now, here, yes, I did turn friction off. Most of the time you would have, it's called dampening, as time goes on. Obviously the pendulum wouldn't keep on going, but the main idea that I want you to understand is this transfer of energy here, that the energy switches between kinetic and potential, but the total energy always stays the same. That's what I'm wanting you to understand. So with this, they switch places all the time between gravitational and kinetic, and that's a law. It's law of conservation of energy. It's that energy cannot be created or destroyed. Never. So one of the really, really cool ideas about this is that think about at the very, very beginning, Big Bang, that there's this huge amount of energy outputted. You and I are using that exact same amount of energy to move, to listen, to speak, even today. That it literally is that energy cannot be created and energy cannot be destroyed. It's always what we call conserved. So in those two graphs, the pie chart never changed size. It didn't get bigger or smaller. In the pendulum, that the total energy graph never changed. It's because they always remain constant. The system, as long as it is closed, meaning that there's no outside influences, then the total amount of energy will always remain constant. We call that mechanical. So mechanical energy is the addition of potential energy plus kinetic energy, and the amount of mechanical energy always remains the exact same. That's what you end up having. So that's the main idea as of right now, is that energy always remains the exact same. Here is a problem of you are going to solve for the kinetic energy of a skydiver. Now I want you to pause the video and I want you to try and solve on your own. So please, please, please be sure to rearrange your problem. Okay? Now, I am not going to give you the answer to this one because I think that it would be more beneficial for you to work with it with someone else in the class. Just be careful about that velocity squared value. Okay? But besides that, I want you to try your calculations for the rest of the day. These calculations are going to look a little bit different than some of the other calculations that you've done in the past, but as long as you follow the exact same rules, you're not going to have any mistakes, any problems at all. So here's the pattern that I want you to do, is that with these calculations, I want you to find a group, try one problem on your own, check with the group, and then move forward. If you can do that by the entire end of the day, then I will be absolutely thrilled. So everyone, thank you so much, and I will see you whenever I return.